Hello, multivariable calculus students. This is Mr. Johnson, and this is the third video for section 11.6. And this will be a pretty short one. We're just going to talk about the tangent plane and the impact that the gradient has on this. I've already hinted at this a lot, starting back in section 11.5 when we talked about the chain rule of the derivative, and I had rewritten the tangent plane in a slightly different form based on an implicit equation and the chain rule shortcut. And of course, I didn't talk about the gradient at that time, but I did set up the equation that you can see in number 19 here from the textbook. This is equation number 19, which is the derivative of f with respect to x multiplied by x minus x sub naught, and so on equal to 0. That form was one that we used in the end or towards the end of section 11.5. And I just want to quickly reiterate that. So the idea here was that if you have an implicit derivative, then you have sort of this general tangent plane equation that we had talked about where you take the derivative of z with respect to x, of x minus x sub naught, plus the derivative of z with respect to y times y minus y sub naught. And that was the very first tangent plane equation that we had in section 11.5, or excuse me, section 11.4. And so as we were building that idea of a tangent plane, once we got to section 11.5, we talked about, well, what happens if we have an implicit equation? So we said, all right, let's let this implicit equation be written in the form of f of x, y, z equal to 0, so that we were able to group all of the variables to one side of the equation. And then when you look at your derivatives, so for example, we have z minus z sub 0, this first derivative, dz dx, by the chain rule shortcut gives us f of x, f of z. So we have a shortcut to the implicit derivative for z with respect to x, and we have the same type of a shortcut for the second one, which is the partial of capital F with respect to y divided by capital F with respect to z, and then y minus y sub naught. So in section 11.5, what I showed you was that you can simply multiply everything by the partial derivative of capital F with respect to z, and then balance the equation. And what you get is this equation that we have now defined in the above example, where you have your partial derivatives of f as the multiplier to each of these values. Now, when you think about it, the gradient vector of capital F, now that we know what a gradient is made up of the partial derivatives of capital F. And so therefore, the elements that you can see in this equation are really just the components of the gradient vector. And when you think back to what we have discussed over the course of this section and the gradient itself, remember how the gradient is perpendicular to a level curve as we look at a surface in 3 dimensions. Well, when we start to talk about an equation of 4 variables, which capital F of x, y, z is technically made up of 4 variables, the gradient vector to this surface is also perpendicular. So the gradient vector is going to be perpendicular to whatever set of variables we're trying to analyze. So for example, if we're looking at a function of 3 variables, the gradient vector would be perpendicular to the level curves. If we're looking at a function of 4 variables, the gradient vector is perpendicular to the level surfaces. So again, this gradient vector, as you can see in this diagram here, that gradient vector is going to be perpendicular to the particular surface at a point. Now, why is that important to us as we talk about tangent planes? Remember, way back to chapter 9, when we write the equation of a plane, we need a normal vector, and a normal vector is by definition perpendicular to the tangent plane. So all of those things work together to allow us to have these equations, and now the tangent plane, which we started studying in section 11.4, and then kind of revamped our discussion with implicit equations in section 11.5. Now with the gradient vector, it is really easy to come up with a tangent plane equation because the components here are just made up of the gradient vector itself. Now, we also may need an equation for, and this goes back to chapter 9 again, but for the normal line, remember the normal line is going to be the line perpendicular to the tangent plane. In other words, this gradient vector is the the slope of that particular line. So the gradient vector is going to be our direction of the line. And if you remember, the symmetric equations would be written in this form where the denominator of each of these is representative of the direction vector, which again in this case is the gradient. And remember, each one of these is equal to t. So in our next example, I'll kind of walk through that just because it's been a little while since we've talked specifically about those types of lines, connected back to chapter 9. But this gives a nice overview, just as you look at these equations and the picture there, of what impact the gradient has on the tangent plane. Basically, the gradient makes it much easier. Okay, let's look at just two quick examples. All right, example 1, we're going to look for the equations of the tangent plane and the normal line at the particular point given the equation. The first step is to set the equation equal to 0 and rename it as capital F of x, y, z. So in this case, all we're going to do is simply subtract 3. And then our next step would be to take and find the gradient vector of this particular function, because remember that's going to be how we're going to come up with this equation of a plane. So we have, let's see, x over 2, and then 2y, and 2z over 9. And then we're going to evaluate this at -2, 1, -3. So then for our gradient vector at this particular point, we get -1, 2, and then -2/3. All right, we'll use that here in our equation. So with our equation, we have -1 multiplied by x plus 2. So again, I'm using our point here. So it would be the x value, which is -2. So it's x minus -2 multiplied by -1. And then I have plus 2. So that's going to be coming from our gradient vector, the second component there. And then it's going to be y minus 1 as quantity. And we have then -2/3 times the quantity z plus 3, and it's all equal to 0. So that is our plane. Okay, now for the normal line. Now remember, we have our slope or our direction, which is the gradient vector, and then we have our point. We could write this in a variety of ways. If you remember back to chapter 9, we had x equal to the x value, which is -2 minus 1 times t. And again, that -1 comes from the gradient. And then we have y equal to our y value, which is 1, and then plus 2t, and z equal to -3 minus 2/3 t. So again, just a quick review, each of these values are going to be a point on the line. Obviously, I used this point because that's what was given to me, but any point on the line. And then remember, these values multiplied by your parameter is going to be your slope. And you could put this into symmetric form, which is what was given on the previous page. And that simply is just the process of solving each of these for t and then setting them equal. This last one you could write a variety of ways. You could divide by -2/3. You could, rationalize that in some way and just kind of make it a single fraction, but I'll just leave it as is. So there's going to be the equation of your normal line. All right, let's try one more. This is just a different function, that's all, different point, and we're going to do the same thing. So again, the first step is set this equal to capital F of x, y, z equal to 0. Next step is to take the gradient and then evaluate that gradient at our particular point. That gives us 4, -5, and then -1. And then we'll go ahead and write the equation of the tangent plane. So we have 4 from the gradient, x minus 2, minus 5 from the gradient, and then y minus 1, and then -1 from the gradient, and then z plus 1 equal to 0. So that's your tangent plane. Certainly, I think it seems, or hopefully it seems much easier, the more that we've been able to build the concept, this gradient really helps to simplify that tangent plane equation, which is helpful. I think it was probably much harder back in section 11.4. And then for the symmetric equations of the normal line, we have x minus 2 divided by 4 equal to y minus 1 divided by negative 5 equal to z plus 1 divided by negative 1. And that's it. That's going to be the end of section 11.6. Thank you.